Oh, okay. Um, so before I start, you know that we have split the marks into 50 marks for end semester, 30 marks for mid semester, and there is 20 marks left. Okay. So that I usually give an assignment, something that requires a little bit of work. So maybe not tomorrow. The class after that, I'll give you the assignment. Maybe within 1 week or 2 weeks. 2 weeks you submit it. Okay. It'll be a big problem which will combine a lot of things. So you'll have most likely we'll have to do computer programming and all that and do that, because last time, for instance, what I gave was like a M curve. Okay, I gave some vessel, you have to draw the M curve. That means you will have to first calculate it. It's much easier to do it using a computer. You put those equations on a program, you can just get it, or at least an Excel sheet. Okay, so that's the easiest way to do it. So I'll give you the problem in 2 classes. So you submit it within 2 weeks, and that will be 20 marks. Okay. That and all I don't care. You must be knowing something now. Fortran or C or something. Nothing like that. It's not that I expect you to program using. I'm not bothered about the programming, but to draw a very nice looking graph, it's better to do it in a computer always instead of. That's all. Whatever method some people do it in MATLAB. Last year, some people did it in Java and all. It's up to you. Whatever you know, you use that. Okay. Just do it using whatever is most comfortable, but the problem needs to be solved. That's all. Okay. Now. Let us look at the next one. Now, suppose that a vessel moves from a water of density rho 0 and it moves into another water of density rho 1. For instance, a ship that is traveling moves from what is it called? It's called some kind of lake before it reaches the sea, and then it moves into the ocean. For instance, something like that. So it produces a sharp change in density, and when such a change in density occurs, what will happen? First of all, a parallel sinkage will occur. You know that, because the upward force or the buoyancy force is given by rho into del. Del is the underwater volume, rho is the density. So if the density changes, for instance, if it increases, if the density increases, obviously the buoyancy increases, therefore a draft increases. Okay. So, and another thing happens parallelly, when the density changes, one more thing that will happen is that because of the sinkage of the ship, you know that a small amount of volume is added at the top. Now we can assume that this amount of volume is added at the center of flotation. Center of flotation is the centroid of the water plane area really, but it can be assumed to be the center of that volume. Okay, that is come at the top. So you can assume that this much of volume, new volume, has been added at the center of flotation. So in general, you will have B, the initial B, the center of buoyancy, somewhere to the right or to the left, most likely to the right of the center of flotation, right? So what now here a new volume is added. Now what will happen? It will trim. So because of a change in density, it will trim. Okay, when you, of course, you can directly by intuition you will see that when there is a change in density, there is a sinkage, that is sinkage or rise, that is directly coming from intuition. But if you know the mathematics, you can also see that there will be a trim also. The ship will go down or up depending upon the, well, it will come down only, because most likely the center of flotation, in most cases, almost 75% of the cases, center of buoyancy will be to the forward of the center of flotation. It is always like that, it comes like that. And obviously volume is added at the center of flotation. Of course, it depends whether the volume is added or subtracted. That is the thing, that depends upon whether the density has increased or decreased, like it has moved from a lake to a sea or from sea to the lake. That makes a difference. If volume is added, so obviously volume is added at the aft, therefore the center of buoyancy moves like this. Okay, so more volume at the, so it sinks by the aft or trims by the aft. More volume at the back means it trims by the aft. So, this is a process of change in trim due to change in density, and just to draw this, I will just draw just to make it clear. Okay, now initially there is a water line W0 L0. This is the initial water line, and the ship has a center of flotation. Let's say it's here. Okay, this is the center of flotation. Initially, it's here F. It's in this vertical line. Then let's say that it's initially in a condition such, it will always be in a condition such that G and B will be in the same vertical line, because otherwise it will trim further. So let us suppose that this is the initial B. Okay, let me draw it here. Let us suppose that this is the initial position. Okay, B0, then some G is not changing here, G, and this is the initial state. The ship is initially that center of flotation F, B0, G. Okay, and then it moves into a water which has higher density, as a result of which it sinks further. It sinks further, no? If it is, oh, higher density means higher buoyancy. Okay, it will go up. Okay, that's correct. If it is a lower density, it will sink further. Yes, lower density it will sink because the buoyancy will reduce. Okay. So this is the center of flotation at that point F, and now the B moves to the, as you can imagine, there is an increase of volume here. This is the increase of volume, small v, and so B0 moves to B1. G doesn't change, it is the center of gravity. Then so that itself you can see B and G there is different. So there is a trim. A trim has to occur in any way. Okay. Now because of this addition of volume at the center of flotation, B has moved here, and now the ship obviously trims, and in this case so the ship trims like this. This should go down because V has been added here. V has come, this is moving right. It will trim like this. The ship will trim to the aft. It will trim like this. Then same things we can do. Let's say that the distance between this and the center of buoyancy initially and the F is D, and therefore we can see that the change of buoyancy, not buoyancy, change of the center of buoyancy is B0 B1. Therefore we see that a volume V has been added and a center of buoyancy has moved from B0 to B1. So there is a shift B0 B1 in the center of buoyancy, and okay, now with this data let us do the thing. Now a small volume V has been added. Okay. Now what is the this doesn't seem correct. The distance through which the center of buoyancy has moved, B0 B1 will be equal to, let me see this 1 minute. That means a small volume V is added at a distance D. It has moved a distance D. A small volume. So what we see here is that that's correct. A small volume V has been added a distance d from the center of buoyancy. Okay. So as a result of which the center of buoyancy moves B0, B1 is equal. It's just like the center of gravity. Okay. Center of gravity has shifted from G0 to G1 by that same thing. Del is the volume of the ship, initial volume of the initial displacement of the ship. So del plus V is the final displacement of the ship or the displacement volume of the ship. So V into D, this will give you the shift in the center of buoyancy. Now, therefore, the moment causing trim we can write as W, the weight of the ship, into B0, B1. Okay. It is due to this change of volume that there is a shift in the trim. So the moment is produced due to this shift in B0, B1. Because so therefore W into B0, B1 will give you the moment causing trim, and therefore the change in trim becomes W into B0, B1 divided by MCTC. Okay. This is the direct formula. We say that the change in trim is equal to the moment producing the trim divided by MCTC. Moment producing trim is W into B0, B1. Change in trim. This is change in trim. You are talking about change in draft. This is change in trim. Then, okay, then we can write one formula. We know that the initial weight is equal to the final weight, that is the weight of the ship. So you can write like this. Let's suppose that D0 is the initial displacement of the ship, initial draft of the ship, and let's suppose that S draft has increased. It is the increase in draft. D0 plus S into rho 1 will be equal to D0 into rho 0. Here we are just saying that W is equal to W. Okay, means initial W, the weight of the ship, is equal to the final weight of the ship, or volume into displacement initially. You know that the weight of the ship is equal to weight of water displaced. That is Archimedes principle. Now weight of water displaced is del into rho always. So just initial del into initial rho is equal to final del into final rho. So just do a little bit of manipulation. You will get S is equal to D0 into rho 0 by rho 1 minus 1. So S is the change in draft, means ship is like this. Initially its draft is D0, and then the ship sinks further, its draft increases further by S, and therefore D0 plus S is your final draft. Now this increase in volume or the increment in volume can be found from V is equal to sinkage. This is your sinkage. S is your sinkage. Sinkage into, actually what should it be? Sinkage into area, obviously. Which area? Water plane area. It's the water plane area. So sinkage into water plane area will give you the, so this is like S into, let's write it as AW. Now in the beginning we derived an expression for what AW as, do you remember this? There is an expression that water plane area is equal to TPC into 100 by rho 0. You did it for mid semester, so I think you should be remembering it. It's not at all difficult. It says that, you know, if there is a unit change in draft, we did that. TPC is due to a unit change in draft. So if there is a unit change in draft, what is the change in volume? So you equate the two, you will get this expression. So S into TPC into 100 by rho 0. This gives you an expression for the increase in volume. So we have seen some methods till now whereby you can find the increase in, or you can find the sinkage. W by TPC is one of them. Okay, that is the main way of finding the sinkage. So once you have that, you can use these expressions to find the increase in volume. Yeah. No. TPC into 100 by rho naught is AW, the water plane area. Now this expression, this is exactly like this. See, there is an AW also here. It's not exactly this, but and this, I mean, this should be AW plus the new AW, which is, but we are assuming it to be almost same, okay, because water plane area doesn't change much because of change in draft of probably 10 centimeter or something. It doesn't make any difference. The real expression is like this. Okay, the real expression is like this. So del plus V is equal to del into rho 0 by rho 1, or V equals del into rho 0 by rho 1 minus 1. So we are just having a couple of similar formulas for, we are having a couple of formulas for, so you know, and we have this expression, we will need this for the few problems. So this is needed. This is very important. Okay, W into B0 B1 by MCTC is the change in trim. Okay, there is a problem. Now, okay, so a vessel is, you are told that a vessel has a draft forward equal to 8.72 meters. It has a draft aft given as 9 meters, and it is in a water of density 1.025 tons per meter cube. This is the initial density of salt water. Now it enters a dark water of density rho 1 equals 1.004 tons per meter cube. Now you are asked find the draft forward and aft taking account for the change in trim due to the change in density, and you are told MCTC is equal to 162 tons per tons meter per centimeter, TPC equals 29.8 tons per centimeter, LCF is equal to 82 meters forward of AP, LCB equals 90 meter forward of AP, length of the ship is equal to 170 meters, and displacement of the ship is equal to 27,000 tons. Okay, so with this data you are asked to find the change in or you are asked to find the change in trim, and finally the final drafts due to the ship moving from the salt water initially at a density of 1.025 into ordinary water of density 1.004. Okay, so now first of all you need to find the amount by which it will sink due to what is it given? Okay, that's what you, I mean, you have to find the amount by which the ship will sink. So you have to find the initial draft and the final draft. Note, we always find the sinkage or the S in this case by taking the mean draft. Okay, we never took the aft forward or any, we usually take the mean draft, and it is the draft at the center of flotation. So we say that if the center of flotation has sunk by so much, that is the parallel sinkage. That is the amount we call as, that is what we call as parallel sinkage. So the draft, the mean draft initially is equal to this formula. I mean, you just have to remember T is the trim. I mean, I'll just repeat, there are two things here. There is a trim and there is a change in trim. This is the trim. Trim is the difference between the forward and aft drafts. That's all. And change in trim is the change in that trim, or rather. Okay. So DMI is equal to DA minus L by L into T. So the draft aft is given to be 9 minus L is the these things should be clear. L is the distance of the LCF from the aft perpendicular. It's given as 82, and L is the length of the ship 170 into T is the trim, that will be the difference between the forward and aft drafts. 9 minus 8.72, what is it, 0.28. So this will give you the mean draft initially. It comes to 8.865 meter. So this is your initial draft, mean draft. Then since you know, where is that formula? Okay. See, since you know the change in density, means since you know how much is the initial and final densities, you can directly find the this S from this. You know D0 initially. Note that this D0 is the initial draft at the mean point, and that is at the center of flotation. That's what we just calculated. Now we can directly calculate this S. So S is equal to just do this initial mean draft into 1.025 divided by 1.004 minus 1. Therefore, it becomes about 0.185 meters. So this is the amount, 18 centimeters is the distance by which your ship will sink. The mean point of the mean draft will sink because of this change in density. That is the first thing. Then another thing is del, which is the initial volume of the ship, is equal to W by rho 0, which you can directly calculate. W is given 27,000 tons divided by rho 0 is 1.025 tons per meter cube. That will give you. So this is the initial volume of the ship. Now again, from this formula we can find the increase in volume. So V, the increase in volume, just do this del into rho 0 by rho 1 minus 1. So this will give you something. So this much is the increase in volume due to the change in density. Now the ship has, this is parallel sinkage. Now there will be trimming. Okay, that is the next thing you have to calculate. Two things you have to do whenever, in case of change, in case of load added or in case of change of density, both are exactly same. There is a change in the only difference is that in case of load added, you say that the moment changing trim is equal to W into shift in G0 G1, means shift in the center of gravity, because or the shift or the weight or the distance through which the weight is shifted, the W into D, that is the distance through which the weight is shifted or the distance through which the center of gravity shifts, divided by whatever, and that will give you the moment changing trim. But in this case, when there is a change in density, you do not use G, you use B, because volume is changing as a result. Because of this change of volume, there is a change in trim, and therefore in loads you have G, in density you have B. That's the only difference. Everything else is exactly same. Now this B0 B1, even the formula for B0 B1 and G0 G1 are more or less same. Instead of volume, you put the weight. That is only difference. V into D by del plus V is equal to, so V is given, and we have to find B0 B1, the distance through which B has shifted. How much is that? LCB is given, that is initial LCB is 90 meter forward of AP. We need to find V into D. D is the distance between LCB and F, right? 90 minus 82, yes, 8, correct. So this will give you the B0 B1 divided by this 2634 1.5 plus 551. So when you do this, you will get your B0 B1, the distance through which the center of buoyancy has shifted, 0.164 meter. Now and then next is trim is equal to moment changing trim divided by MCTC. Okay, it is the moment changing trim by MCTC. The moment changing trim is equal to W into B0 B1 divided by MCTC. W is equal to the weight of the ship, 27,000 tons, into B0 B1 we just calculated, divided by MCTC. MCTC is given. So this will give you, okay, so this will give you the total trim, and now we need this is the change of trim, not trim, sorry. This is the change of trim. Now we need to find the change of trim aft and the change of trim forward. I mean, our purpose is to find the final draft forward and aft. So we need to find the trim forward and aft. We have found out the parallel sinkage. S we have already found. Now we need to add the parallel. We need to find the trim aft and trim forward. Add it to parallel sinkage, and you add to that the initial draft. You will get the final draft. Okay. So this is the change. Then this formulas also we have used. So the change of trim aft is equal to L by L into change of trim. (82 by 170 is the length of the ship into change of trim. We just calculated. Correct, sorry. 27.3 we just calculated in the previous thing. So this is the change of trim, total change of trim. So change of trim into L by L, where L is the distance of the center of flotation from aft perpendicular, capital L is the length of the ship. So you do this, you will get 13.2 centimeters. This will give you the change of trim aft, and the change of trim forward will be L minus L by L into change of trim. That will come to something 14.1 centimeter. Now all you do is if you add to the initial trim, initial drafts, you add the parallel sinkage. In this case, parallel sinkage, it is sinkage because the density has decreased, so it is sinkage. So there is an increase in draft, but something is slightly confusing me here. Wait a minute. It says that the ship has gone down at the forward. Now I have to see why. That is, aft is come up and the forward has gone down. Here B has moved to the aft. B has moved to the aft. How is the ship trimming forward? This I have to check why it's so. It doesn't seem directly obvious. Okay, this I'll check and tell you. But it, according to them, they are saying that the ship trims by forward, not by aft. Even though the center of buoyancy has moved backward, in fact. Okay, let me check that. Is it a mistake here or is it correct? Anyway, I'll check that and tell you. Because accordingly, more volume is added at the aft. No, nothing like that. There is no balancing here. This is just a case when the ship has moved from one density to another density, and as a result of it, what we saw was that the B, center of buoyancy, has shifted backward to the aft. If the center of buoyancy has shifted to the aft, it seems to me like volume is added in the aft, obviously, otherwise B won't shift there. If volume is added at the aft, that is but due to parallel sinkage. Will it trim forward or backward? Now that increase of buoyancy is due, no, it's an increase of buoyancy, I didn't say right. See, there is an increase in volume at F because of parallel sinkage, not because of trim. Because of the density changing, it is first, parallelly sinking, then it is trimming. So because of this parallel sinkage, a weight is added here. We can draw this and see. Let's see, this, for instance, if this is F, if this is B, B1, and if this is B0, weight is added here. This is parallelly sinkage. Now the question is, by which direction does it trim? See, we can see one thing. The force acting is buoyancy into initially it's like this, now it's like this. I think it will trim by forward. See, that is this is correct. See, that is initially, okay, look at this figure. Initially it says that F is the center of flotation. Initially F, it is obviously you have to take the moment about F because it's trimming by F. So F into this distance, FB0, this is the initial, it is higher. In this case it's lesser, okay. So there is a moment acting like this, means the moment is like this, or rather the moment like this is decreased. That is a better way to put. The moment is like this initially, the moment is lesser because the distance has decreased. So that means it's like a reverse moment acting like this, okay. So this will go down. It's a little tricky thing, I also forgot them. Now it's like this, sure. So I think in the initial also I told you. So the ship, when it goes from higher density water to lower density water, first of all it will sink and it will actually trim forward, okay. It will always trim forward. It's because of this. This is initial B0, this is B1. The weight has, that is what caused confusion. It is due to parallel sinkage that, see, because of the increase in volume at F, there is a parallel sinkage, as a result of which B increases. That doesn't say anything about trim. It is just due to parallel sinkage. That is a different thing. Now we have to find what is the direction of trim. That is like this. Trim is occurring due to the buoyancy here. At B0 it's like this, at B1 it's like this. This distance is more, so the initial moment is more, the moment has decreased. Whatever is the moment initially in salt water has decreased in, so the moment which made it trim like this has decreased, which makes the moment like this has come, okay. More or negative, less, negative is less, that means positive is more, same, that by that concept the ship will trim like this. So you have to add trim forward and subtract the trim aft to get your final draft here. Final draft, this is forward, you have to add. Remember, whenever the ship goes in, you are adding the trim to the draft. Whenever the ship goes up, you are subtracting that. It's obviously like this. That is, sinkage is when the ship comes down like this. That is plus always, okay. That is an increase in draft. You can see it's an increase in draft. Similarly, trim like this means here it's an increase in draft, here it's a decrease in draft. So here it's plus, here it's negative. So in this particular case, the ship trims like this, and so this you have to add. This is how you find the draft forward and aft. At forward you add it, and at aft you subtract it. This is what happens when you have density change. That is one possibility. Then Okay. Then okay, using this formula, there is another problem, that is, you are told that a ship is floating at draft forward equal to 5.8 meters, at a draft aft equals 6.6 meters. Now you are asked to find the position of the longitudinal center of gravity, means find LCG, and you are told that the length of the ship is 174 meter, and some hydrostatic data are given, like you are told that LCF is 3.7 meter. See, there is a figure like this. You know what this means, right? This means midship always. You can look at any figure in ship drawings, you will see this. In the drawing itself, you will put this figure. It means midship. So LCF is 3.7 meters from midship. So that's what that figure shows. Okay, then so we know we know what is LCF from midship. Midship is obviously half the length of the ship. So total length of the ship is 174. So if you want, first let's find LCF from aft perpendicular. It will be L by 2 plus this 3.7. So that will be 90.7 meter. Now let us find the mean draft. Note that whenever you are doing anything with draft, find the mean draft anyway, because whatever you do, in most cases you will have to find parallel sinkage, or what else? In case you need to find the change in trim, anything, you need to find the mean draft at all costs, and don't take mean draft as an average of the two drafts. Use this formula. Okay, we derived the formula. So use this formula, dA minus L by L into T, where T is the total trim. Trim is again defined as the draft forward minus draft aft, or okay. So this is equal to draft aft is given, you are given the drafts in the aft and forward direction, minus L is the distance of LCF, so that is given 90.7 divided by L 174 into this is 0.8. Now again here note that this small l is always the distance of LCF from the aft perpendicular. So such a few things that just has to be by hearted, I mean just memorize. So 6.6 minus this thing, that will give you the, so this gives you the mean draft. Now once you have this, you are given, okay, I didn't write it there, but MCTC is given. Okay, MCTC is 356 tons meter per centimeter, and W is equal to 21,500 tons. This is also given. Then okay, this is also given, I didn't write. LCB is equal to 5.2 meters forward of same thing, okay, midship. So you are told that LCB is 5.2 meters forward of midship. Now we can use the formula, the distance through which, means we have this formula anyway, W into B0 B1 divided by MCTC is equal to trim. Okay, this formula we have. I'll just change it around. Therefore B0 B1 is equal to trim into MCTC divided by capital W. So this will give you the distance through which the center of buoyancy is shifted. No, it's not the change of trim, it's the trim. See, if it is at even keel, you have something like this, you have a trim, forward minus aft, draft forward minus draft, or draft aft minus draft forward will give you the trim. So, in this formula, that is what, please study this carefully. Okay, this people make lot of mistakes here, because there are, as I said before, there is one thing called draft, there is one thing called trim, and there is one thing called change of trim. Three things. Okay, draft is where the ship is, or the depth, or the final depths to which the ship is, that underwater portion is, that is called the draft, and that has trim, which is the difference between the draft aft and draft forward. Okay, and then if something happens to the ship, like loading, or something is loaded on the ship, or it changes the density, then the initial trim will change to a final trim. Okay, that is a change in trim. And of course, then there is parallel sinkage, is the distance through which the draft mean draft, or the draft at the center of flotation, comes down or goes up due to the loading. So, you have B0 B1 is equal to T into MCTC by W. In this case, there is no change in trim. We are not talking about any change in trim. We just have a ship that is in some trimmed condition. It has some initial draft aft, initial draft forward. You are just asked to find its longitudinal center of gravity, provided you are given some hydrostatic data like LCB, LCF, etc. So, B0 B1 is equal to trim into MCTC by W. T is the trim, all these things we have. Therefore, this comes here, meter. Then now what we are seeing here is that, see, we have assumed that, of course, it goes without saying, the ship is in a stable condition. Okay, otherwise you cannot do this problem. Means if it can still trim or go to some other given keel, it's a different problem altogether. So, what we can say here is that ship is initially, it was designed, it was put here on the ship, on the sea with some loading, and then it trimmed to some angle. Why did it trim to that angle? It trimmed because it is trying to bring its G to the same point as B. It will trim that much, such that G and B are on the same point, and once it becomes in the same straight line, there is no more any moment, and it's stable as far as rotation is concerned. Okay, and two things, actually, when you put a ship on sea, two things will happen. It will adjust itself such that its weight is equal to the center of buoyancy first. Therefore, it will design its draft as such. It will design its draft, it will go down so much such that its weight of its buoyancy is equal to this weight. Okay, so when you put the ship in the water initially, after you design it, if you designed it properly, then it will come to its when you are designing itself, you actually design the draft. So, when you properly design, to that design draft, it will come and sink. At that stage, your buoyancy will be equal to your weight. That is the first thing that will happen. Then the ship, nature will check if the LCB and the LCG are in the same position. If it is not in the same position, means in your initial design, you have made a mistake. A ship should actually look like this. In its load condition, a ship should, at least in its design load condition, the ship should look like this in an even keel. If it is not, that will happen if its LCG and LCB are at the same vertical line. But if it is not, let's say that LCG is forward, LCB some difference, then immediately the ship will, that difference in moment will act. One force acting down, one force acting up, separated by a distance, producing a moment. So, it will trim. It will trim to such angle such that these two come in the same straight line again. At that angle, it will be stable. So, these things you have to check while you are designing the ship, so that the ship is initially at the design draft. This is how you design a draft, for instance. This is the only way. You put weight is equal to buoyancy, you will get, this is the draft that the ship should be when it should go into this water of this density. So, same thing here so that is the same thing happening here. The ship has now come to some stable state. So, we say that the distance through which B has shifted from its initial position, LCB, so we can assume that this is a faulty design if you want, okay, such that because of the design, LCB and LCG didn't come at the same place, or maybe you added more load than the design itself says. Design says that the weight is so much, you added more load, whatever it happened, LCG didn't become equal to LCB, as a result of which B shifted to reach G, and so it moved this much distance. So you can find that your LCG should be, it has shifted this much. Your center of buoyancy shifted so much, which means this is the final position of your center of gravity, meter. And if you just add an L/2 to it, you will get the distance from aft perpendicular. This is the distance from midship. You see this figure. So LCG, you add 87 this thing to this 3.875. So you get your 90.875 meter. So this gives you your LCG. Okay. Then one more problem, that is your so you are told that there is a vessel that is floating at draft forward equals 2.9 meters, draft aft equals 4.7 meters, and the length of the ship is 174 meters. Then you are told that there is going to be a loading of cargo. I won't write the whole thing, but you are loading some cargo. So like this. So this is on your compartment 1, you are adding 3,800 tons, and its distance from the aft perpendicular is 146 meter. So like this you keep adding like this. Okay. So this you are told. So initially you have ship in some trim, and then you add a lot of weight. Now you are asked the final draft on once you have loaded the whole thing, what will be the final draft. Now so as we can guess, first we have to find the initial LCG. We can do one thing. Let us assume that the ship, it's just this previous problem. Okay, so you have the ship, you have not put in these loads. Before that you have the ship, you put it in sea, and it is said that when you are given a problem like this which says that a ship is floating at that draft, it means it's in a stable state. So it is said that the ship is floating in that draft. We are given the forward draft and the initial draft. That means you are given the trim. So you are given the initial conditions, and when it is in this stable state, we can automatically assume its LCG should be equal to its LCB. Okay. So first we have to find, first we will see in even LCB when you are given will be the initial LCB. Okay, I'll tell you, that is, see, you are given here, this probably will be given LCB. LCB is given. This is a hydrostatic data. Hydrostatic data means it is the data when the ship is in an even keel, that is when you are designing it. Hydrostatic data is always the data that you are given when you are designing a ship. Means, for instance, ship, you have designed the ship, you are always designing the ship for an even keel. So you are told that, if you are told that from the hydrostatic data the LCB is so and so, the meaning is that when the ship was in an even keel, its LCB was here. Okay, that is the value given. But see, this problem says that the ship has trimmed, it has trimmed. That means LCB is no longer at that value, LCB has shifted. Okay, so that is very important. Though you are given the LCB, it's not the final LCB in the trimmed condition. It is just the LCB given by the hydrostatic data, which means LCB in an even keel. When it is designed, a ship is always, whether it is faulty or not, they have designed it for an even keel. Okay, a ship is always designed for an even keel. So you design it in that condition, but because it's, maybe it's because it's faulty, it trims and the LCB shifts now to some new point. Okay, that new point you do not get from the hydrostatic data, that you get from some other value. And the additional thing that you need to know is it has trimmed so much such that its new B will be directly below or above G, or maybe at the point of G. Okay, that is the important thing. Two things, hydrostatic data means even keel. That LCB that you are given from hydrostatic data, do not take it as the position of the center of buoyancy when the ship is in a trimmed condition. That is wrong. It's not like that. LCB is the LCB given from the hydrostatic data is the LCB when the ship is in an even keel. Then you are told that the ship is trimmed. That itself says that the buoyancy has shifted from that position. It has shifted to some other point, and it has shifted so much so that finally your B is directly above, on, or below the center of gravity. Therefore, you know how much where the center of gravity is from this. By working on this, you will get what is the center of gravity. Okay. I'll just do the first part. We'll complete. So now you know what the problem is. So first, you are given all these hydrostatic data. So first, what you need to calculate is your first LC from all the you need to find the distance through which the center of buoyancy has shifted. B0, B1 has shifted. That you need to calculate. Next, from B0, B1, you find the final position of LCB, or LC. In what you have is LC B0. Find LC B1. Okay, final position of the center of buoyancy. Now that LC B1 will be equal to your LCG. Okay, so you have your initial position of the LCG. Initial means you have after trimming, you have the position of your LCG. Now loads are added at different points on the ship. At different longitudinal positions, loads are added, as a result of which your LCG changes again. Because of load adding, the LCG will change. So LCG comes to a new position now, and so that will give you your new position of LCG. Okay, and now you go exactly backwards from the problem. I mean, what we did initially, from that LCG, you find B0, B1. Okay, you find the distance through which it will. You go backwards to find B0, B1. From B0, B1, you go backwards to find the trim, and from trim you add and subtract the trim to get the final drafts. So it's just going backwards. So I'll stop this here. I have somewhere halfway between the problem, but I'll stop this here. Okay, thank you.